Welcome again, week 4, the exact science of the hard matter, examining, controlling, verifying. Today we will continue our discussion. Last week we examined some brief elements of neuroanatomy and physiology. Today we will talk about developmental neuroscience, we'll talk about neuroengineering, and a few other things that are connected to the scientific method as we use it in critical neuroscience. Wonderful. So last week we briefly talked about neuroanatomy, and today we will continue our discussion on cellular and molecular neuroscience. So one of the things that I would like to start our conversation with is the structure and function of basic neural structure, axons, dendrite, and so on and so forth, similar to what we briefly discussed last week in the context of basic structure of neural transmission. So if you remember, we started with a distinction that has to do with the structure and the morphology of neuronal cells. And if you remember, we mentioned that neuronal cells can be unipolar, pseudo-unipolar, they can be bipolar, and they can be multipolar depending on the structure and mutual relation between axons and dendrites. Another thing that I want you to remember is that there are neurons with long projecting axonal processes beginning the gray matter of the central nervous system, and those are referred to as Golgi 1, and together with a short axon Golgi 2, they represent multipolar neurons such as the granule cells. Now, of course, in this video I will not examine every single neural type, for which I will encourage you to review the textbook, and part of this will not be discussed as part either of the weekly quizzes or reading assignment, but this is just something to keep in mind as you continue with the knowledge of cellular molecular neural cells. So one of the things that you could keep in mind is that that there are neurons such as the basket cells, bat cells, anterior horn cells, median spiny neuron, Ranchian cell, and spindle cell. But there's also something else that has to do more with chemistry, with cytochemistry. If you remember, last week we talked about neural transmission as a tripartite combination of electric activity, electrochemical activity, and this activity is predicated upon the function of neurons, axons, dendrites, and if you remember, we also mentioned the action potential. Now, of course, whether you want to take this electromagnetic chemical perspective or you want to distinguish each of these parts, it's really important to have a basic knowledge of chemistry in this sense. And for the sake of this conversation, just think about some subdivision that are fundamental, such as endaminergic, cholinergic, dopaminergic, GABAergic, glutamatergic, monoaminergic, nitroxidergic, peptidergic, and serotonergic neurons. And of course, on those situations, you have to think about GABA, you have to think about serotonin, you have to think about dopamine, and I would really encourage you to review the basic function of each of these neurotransmitters, which you will find in the link below this video. Again, so gamma-aminobutyric acid, dopamine, serotonin, adrenaline, so on and so forth. Now, within cellular and molecular neuroscience, is there anything that we can use to investigate these properties, similar to what we said in the previous week regarding brain imaging? If you remember, we talked about fMRI, MRI, SPECT, and so on and so forth, CT scan, etc. Now, the answer is certainly yes, and if you think about there are elements from molecular biology and pharmacology, but the specific techniques utilized in cellular neuroscience to investigate neurons include confocal imaging, intracellular recording, electrophysiological techniques, for instance, patch clamp and voltage clamp, and 2-photon laser scanning microscopy. Now, we utilize this technique to have an ulterior precision in the sense that they allow for a very detailed analysis of neuronal function, excitability, synaptic transmission, myelinating processes, action and gradient potential, and cellular response to polarization and depolarization through threshold, rising phase, falling phase, undershoot phase, and recovery. This again will warrant a re-examination of the action potential. Now, since neuroscience is a field that cannot be completely distinguished, as in separate from other fields within scientific inquiry. A good way to look at this is from the perspective of endocrinology, epidemiology, as well as if you think about gene expression, because gene expression might influence a wide range of brain functions. And molecular neuroscience does study epigenetic mechanisms of regulation for this reason. It studies these mechanisms, it studies DNA methylation and histone modification, and in order to isolate, to specify specific markers. Now, this approach has an immediate application in the study, and it also has an application regarding mental health disorder, as well as neurologically based disorder. Think of it as Alzheimer's, for instance, but also any type of neurodevelopmental issues. And this is exactly the next topic. We're talking about developmental neuroscience. And developmental neuroscience also in connection to other fields of human development, so human growth of development on one side, and developmental psychology, including psychopathology, on the other side. Now, since we mentioned Alzheimer, the progressive loss of both cognitive functions and memory affecting patients with Alzheimer's disease has a complex etiology linked to several neurological or genetic hypotheses, including the cholinergic, the amyloid, and the tau hypothesis. A GABAergic mechanism, as well as a dopaminergic component, is found in Parkinson's disease instead, in the specific loss of dopaminergic neurons in the substantia nigra pars compacta. Another example is the absence of normal inhibitory inputs from medium spiny neurons of the basal ganglia as a cause of Huntington disease. In the case of excitotoxicity instead, the primary damage to neuronal cells comes from excessive stimulation of NMDA and AMPA by glutaminergic form. This is the same family of ionotropic glutamate receptor, for instance, kainate. Now, when we think about neuroscience, we think about building blocks. And those building blocks are cells, of course. Now, if we think about cells as this primary element, these building blocks of the system, and by cells, of course, we mean neuron, you think about this whole structure that determines those processes that we just mentioned. And this means also that cells are a contributing structural factor for the preservation of health. And from the perspective of medicine and neuroscience, health really is connected to homeostasis, to the homeostatic processes in our body. Now, think about injuries that are at the level of the central nervous system, which represent a challenge for the development and maintenance of normal neuron functioning. So as cells' membranes are constantly morphing to adjust to the homeostatic processes within the organism, connectivity and permeability are among the fundamental factors and functions in the preservation of health at the cellular level. What does it mean? Well, if you don't have homeostasis, when these health levels in the body are not observed, then patterns of cellular injury arises. To give you an example, the deprivation of oxygen supply or hypoxia causes damage to the sodium-potassium pump. We mentioned the sodium-potassium pump multiple times. And this, of course, has sublethal effects. They're sublethal in the sense that are reversible, potentially reversible, but they create damage, for instance, swelling, and swelling is, of course, a common epiphany of the vast majority of cellular injuries. However, when the cause of such hypoxic processes is not eliminated, then the damage becomes irreversible. So when a reduced blood supply leads to arteriosclerosis, cells shift from aerobic to an anaerobic state, and therefore metabolism. Now, if you think about reduced blood supply, you think, of course, of ischemia. This, in turn, affects tissues and increases metabolic acidosis, with a lethal outcome for cells. At this stage, we talk about a permanent pathologic change or irreversible cell injury. Of course, any analysis in neuroscience will not be complete with a thorough examination of the influence of nature over nurture. Now, we mentioned nature over nurture multiple times. We mentioned it in the context of development as well as treatment of mental health disorders. And we mentioned nature versus nurture in the basic debate of this course when you think about a dualistic as opposed to a monistic perspective in philosophy. Now, from the perspective of cellular and molecular neuroscience, this really leads us to developmental neuroscience, because one of the good things to keep in mind is that there are genetic and epigenetic factors. For instance, the arrangements related to congenital malformations and metabolic errors. Now, these factors are responsible for the morphing patterns in the cytoplasmic membrane's shape and structure, as well as receptor or delivery transport mechanisms. Now, besides the damages on the cell membrane, injuries can happen at the level of DNA patterns. The alteration in these patterns is at the basis of misregulation of gene expression found in cancer. Therefore, the progression from reversible to irreversible cellular injury arises through the alteration of the genes controlling the epigenome, thereby disabling the repair function of the DNA. So those are the building blocks. Those are the neurological, anatomical, functional elements that made us who we are. And if we think about a predictive power of neuroscience, specifically in the context of therapy, and even more so in medicine and psychotherapy, then going back to the basic building blocks is the essential thing to do to understand where we are in this spectrum. Now, if it's a spectrum we're talking about, well, this really leads us to an understanding of where we are, where we're headed, but also where are we in terms of increasing steps toward a goal. So if the question is, where do we come from and where do we go? Well, this is the realm of developmental neuroscience and developmental psychology. And one of the things to keep in mind is the difference in terms of theoretical construct between a continuous or discontinuous development. So this is to say, are we developing as human beings through a constant flow, or are there different stages, each of which is completely separate from the previous one? And by separate, I mean you can clearly distinguish the end of the previous one and the beginning of the following one. And this is something that is part of psychology, I would say, is not since time immemorial necessarily, but it's one of the classical constructs in psychology. Just think about the work of Jean Piaget, for instance, or the work by Vygotsky in the context of a socio-cognitive perspective, or the works by Bandura and Michel when you think about delayed gratification, agency, empowerment, and possible obstacles. In other words, whether our observation of cultural, social, and peer-to-peer behavioral patterns plays a role in influencing and conditioning this very pattern. Now, of course, developmental neuroscience, it's not developmental psychology, and so the focus really is in prenatal development by definition of neurological structure. However, because the fact that those factors are so important for the early development of a human being, then the same patterns can and should be observed all the way until adolescence and early adulthood behavior. We mentioned multiple times the role of the prefrontal cortex in the context of one of the last part of the brain to be developed. Now, this is not to say that psychology as a field is not involved and invested in prenatal investigations, and this has to do very often with some elements of transcendental approach to psychology, in some cases along the lines of analytical or psychoanalytic psychotherapy, because of the theories of dreams, because of the attention and focus on preconscious and subconscious state, but also in a more transcendental sense per se. Think about the work by Stanislav Grof, for instance, and the development of pre and post natal behavioral patterns with a solid within this framework transcendental element as a causal factor, including the causal factor that are predicated upon what he defines as psycho-spiritual crisis and the traumatic experience of birth. In this sense, developmental neuroscience really incorporates multiple perspectives. So aside from psychology, classical neuroscience, biology, cognitive neuroscience, because the field really covers the neural development from the ectoderm, giving birth to the mammalian central nervous system, all the way to the specification, migration, and self-organization neurons, allowing for axons and dendrites to further extend and develop into more and more complex synaptic-based communicative system. Now, we talked about dualism. In a dualistic approach, the mind will have to play a fundamental role, either, of course, active or passive, in this very development. This perspective is also providing philosophical basis to the theoretical justification of phenomena such as a placebo or nocebo effect, but also shaping the core neurogenesis and mirror neurons. Now, when placebo and nocebo, we we identify the positive or negative, respectively, constructs in a mind perspective. And the whole idea here is that there is an element of agency that is construct upon this neural development, and yet is also separated from it. So the very creation of a separate forebrain, which is prosencephalon, midbrain, mesencephalon, and hindbrain, or rhomencephalon, to the further subdivision of telencephalon, diencephalon, mesencephalon, metencephalon, and myelencephalon, and their future developments, respectively cerebral cortex and basal ganglia, thalamus and hypothalamus, pons and cerebellum, and medulla oblongata, stems from the processes, activity-independent and activity-dependent mechanisms, some of which are truly cognitive, in the sense of sensory motor underpinnings to behavior analyzed in developmental neuroscience. Now, since neural activity is also a flowing activity, an important factor in this context is the activity of myelin sheath, and how fast and how smooth the transmission of data from the neurological perspective occurs in the brain. So whether those neurotransmitters are actually able to pass a synaptic cleft and deliver the message. Now, in this context, we mentioned multiple times MRI, CT scan, and fMRI and SPECT, but there's a different type of technique that specifically addresses this flow aspect, this myelin sheath aspect. And it's called MCR, or multi-component relaxometry. This is the type of technology that is used to more precisely measure the level of myelin in the brain. And this is very, very important because it really translates into an improved ability to account for possible medical problems, for instance, epilepsy, including, from the developmental perspective, pediatric epilepsy, which is suspected to involve altered myelination in the afferent or afferent white matter pathways adjoining epileptic foci. The same applies to disorders such as multiple sclerosis, which is also associated with gross white matter damage and demyelination, and to a variety of other issues in connection to localization and function versus structure. Of course, studying factors of positive development also means studying factors for negative development, or in other words, monitoring what the normal development of brain function is also means to account for all impediments, obstacles, and damaging factors to this very development, and whether we can account with some level of predictive properties what those damages, what those impediments could represent in terms of the physiological development of the brain of a human being, and what repercussion this will have in behavioral, cognitive, and emotional factors, also from a social perspective, in the way we exist in the world, which is, by the way, one of the central aspects of this course, how the mind-brain problem actually has a practical application in everyday life. Now, if you think about it, this is one of the central elements in neurogenesis. Now, when we think about neurogenesis, when we think about the creation of neural structures, whether we fully agree that neurons rebuild themselves, or what is rebuilt is the whole structure from the synaptic level all the way to the connectivity issues, we can also think of neuroplasticity as a concept. And neuroplasticity is essential from a therapeutic standpoint, because whatever we're doing to help individuals, it really is predicated upon our ability to create something that changes over time. And this has to do with behavioral change, whether we think about classical psychology all the way to coaching techniques. Think about motivation interviewing, integrative health and wellness coaching. When we think about the trans-theoretical model of change, the one by Prochaska and Di Clemente, the idea is that we can change something, the person's mentality, I dare to say. By mentality I mean a mind-based cognitive process and related behavior, if the brain has indeed the ability to reposition itself, rewire itself. I don't particularly like the term rewiring. I feel it's somewhat reductionist and mechanistic in explanation, and to think of axons, even bundle of axons, as wires, it can get the point to some extent from a computational standpoint, but I really feel it misrepresents the system, the way it works, and even the way it is structured. But the idea is this: the brain can change itself, can adjust itself by virtue of being exposed to things, either internally, and this has to do with genetic factors, genetic markers, developmental problems, and different speeds, and the whole discussion we just said about continuous or discontinuous development, as well as by talk therapy, by by stimulation of those mirror neurons that, of course, are relevant to somatosensory elements, to motor elements, as well as to the development of empathy and the ability to exist in the world in a social sense. Now, in regard to neurogenesis, this is one of those fundamental phenomena that occurs at a neurological level. And this starts from the brain, but it really extends to the nervous system as a whole. And maybe from a scientific standpoint, this construct makes a lot of sense. It extends to a combination of multiple systems in the human body. And in this sense, we could say that the organism is by definition a multi-system. And it's a multi-system that really is predicated upon an integrative approach. Think about psychoneuroimmunology. Thinking about what we said about the HPA axis. Think about what we said about the chronic stress response and the role of the amygdala and the cortisol level, and the pituitary gland, and so on and so forth. Now, this activity and influence is related to homeostatic and cell-preserving processes, which provides another element of universal factor in this context. We mentioned that within critical neuroscience, one view that utilizes criticals and adjectives, a view that challenges assumption. It's critical of the system itself. But I also warn against some extreme postmodernist views that will reject even the existence of something universal. And what is more universal than the neurogenetic factors? Now, if you think about this and think about the processes that are, again, related to homeostasis and these cell-preserving processes, you think about cell-preservation as obtained by the regulatory activity of the trophic factor. And this is a hypothesis that was awarded the Nobel Prize. Think about the work by Rita Levi-Montalcini and Victor Hamburger. So this was a very important fundamental discovery because one of the central element in this trophic factor was really the discovery by Montalcini and Stanley Cohen of the nerve growth factor, the NGF, together with the ciliary neurotrophic factor, or CNTF, and the glial-derived neurotrophic factor, which are among the fundamental elements of the process of preservation and growth, as well as gene expression and more generally development. Now, this is fundamental because it gives the idea that the body has its own wisdom. And of course, I am aware of the fact that we shouldn't fall prey of a romanticized or pseudo-poetic attempt to attach external meaning. But what is more clear than a self-preserving factors at a very life level, where the innermost core of the system has a somewhat high versus low, inner versus outer, almost fractal element to reproduce itself. What is more clear than a nerve growth factor in this sense? This really, I dare to say, almost vitalistic principle. And I say this with clarity, but also with some level of theoretical addendum in terms of interpretation, because it seems to me that the existence of this factor really is a good indication of a universal push, I dare to say. I don't want to say craving, pulsion, or any psychoanalytic term, but there is something inside our body that is really prone to be interpreted as inner body intelligence, even when we think about brain intelligence, self-preserving intelligence as the ability to read in between. Now, this is one of the most fundamental questions we have. Are we reading too much into the processes? Are we adding descriptors and justification, causal justification that are not really warranted? Are we, how can I say this? Are we more prone to idealize the process, to say that there is a sacred spiritual force in our bodies that is responsible for this self-preservation, for this development, this evolutionary development of the system? And it is very, very dangerous to attach any external label in science, because this would be similar to saying, I don't know, that the water is wet because of its waterness, which doesn't really make any sense because it's simply a tautological statement. It doesn't really add any type of knowledge, certainly not a causal one. So the same attention and care should be put when we want to push a certain poetic agenda, when we interpret the origin of these developments and these processes. And yet, the very fact that they work, and they seem to work according to very specific pattern, in my mind, is enough justification to at least opening up the perspective of this inner notion of a body intelligence when we think about developmental neuroscience. Now, a question may be, okay, well, if this is true at the level of the individual, we in our body have this universal, I would say, ionic, atemporal capacity to rebuild ourselves, at least to some extent. After all, we're not able to completely defeat Alzheimer yet, I would say. So this inner force, this inner guidance, this inner neurogenesis, neuroplasticity, is this something that can be applicable to human species as a whole, to every single human being? And the answer is yes. Can we interpret that process from an evolutionary perspective, more specifically from a bioevolutionary perspective, as in a perspective that accounts for specific steps in the process that are in themselves ameliorating? Now, this is, of course, a very dangerous claim to make, philosophically speaking, because one of the issues whenever we talk about evolution, a broader context, and we apply that to biological systems, and neurological systems in themselves should be viewed as biological, at least from the perspective of neural underpinnings of behavior, the danger is this. When we think about evolution and we think about a progress in this evolution, the danger is to add that very meaning. Because you might ask, well, it is true that we could have enough claims to say that phase B happens as an evolutionary result after phase A, all right? And the fact that phase C follows phase B after following phase A. So we can recognize an evolutionary pattern. But if we add causal factors that are also qualitatively understood, so we make a qualitative judgment as in phase C is better than B and is better than A, as in we are becoming progressively better. Now that is a qualitative judgment, and the issue is that the process itself might not be able to justify those very patterns according to which we make that judgment. So in other words, if we think about evolutionary neurobiology or evolutionary neuroscience, the question should always be, we can observe certain patterns, but before we make a judgment of the goodness about this development, we should always ask ourselves, where do we get our parameters? Where do we get our patterns of judgment? Where do we get justification to say that this type of evolution is better than any previous type of evolutionary based phase? So this is where we are assessing next in the paragraph, rather in the subchapter on evolutionary neuroscience, in the same chapter we analyzed this week. And we will continue, of course, with a general statement about the interdisciplinary structure of evolutionary neuroscience, because, of course, as you can imagine, there's biology, there's anatomy, and there's chemistry contained in this field. Now, evolutionary neuroscience studies the development on evolutionary terms of the processes and structure of the nervous system, analyzing functional, modular, relational, cognitive, and behavioral aspects under the specific scientific framework that the nervous system, more in detail elaborate, can regulate behavior to the design natural evolution has put into action in order to solve adaptive problems faced by organisms. Now, in this sense, concept and diagnostic terms such as maladaptive behaviors in psychology, psychotherapy, and psychiatry have their evidence-based foundation in these biological underpinnings. So if we think about adaptation or maladaptation, of course there is a judgment. The assumption is that the norm is the good thing. Now, I don't want to be cynical in this sense, or unnecessarily, how can I say this, unnecessarily social activist, and by that I mean I don't necessarily think that using terms such as normal is a bad thing, a morally bad thing to do, because in scientific terms, normal really indicates the norm. You could maybe have a discussion whether norm means the mode, the medium, the average in mathematical sense, but the idea is that there are primarily normal patterns of behavior, patterns of thoughts, and what is, so to speak, abnormal constitutes something of an outlier. It doesn't really follow into the general pattern that is observed so far. Now, if we add a qualitative analysis on this normal, the idea is this: well, what is normal from a neurogenic perspective appears to be the best possible way for the system to work, and what is abnormal constitutes an impediment, an obstacle. So in this sense, we can contribute to the connection between these two perspectives. What is good, it's also functional. What is aesthetically pleasant in terms of the structure itself, the inner structure, it's also adaptive. Now, this is very interesting in my mind because it's connected to the term kalos in Greek, for beautiful and good, and its relative bellum in Latin. So it's a very interesting feature of ancient philosophy to claim that what is beautiful, it's good. And what's good, it's not just good aesthetically speaking, in terms of sensory perception, that's what aesthetic means, so appealing to the eye, but it's also good from a moral standpoint. So you have goodness enhanced, goodness 2.0, so to speak, which is something that at first might be somewhat naive, but naive in a good sense, naive etymologically speaking, so native, originating, I would say even archetypical in a sense. And this is what we are analyzing in evolutionary neuroscience from this perspective. Now, there are discussions, of course, in evolutionary neuroscience, because evolutionary neuroscience is in itself a product of evolution in Darwinian terms, which of course contributes to the specific, the theoretical assumptions, looking biological underpinnings to the neurological base of multiple layers of animal interaction. So in this sense, there are connections between evolution neuroscience and developmental neuroscience, especially if you think about the connection between process and phenomena such as mirror neurons, we already mentioned that, but also psycholinguistic evolution and language acquisition, all the way to modular processing and lateralization of functions. We mentioned Bandura, of course, social and cognitive skills, emotional regulation, relation, empathy, social bonding and cohesion, feedback control and feed-forward control, and then, of course, self-awareness, self-image, self-adaptation, and possibly self-conceptualization, including self-esteem. When we think about those terms, we can think of the two angles. So one would be a categorization of self, and again, from the perspective of evolutionary neuroscience, our self is a result of an evolution. It's something that is in an ongoing process, and of course, this might mean that at some point we might reach the top of the process, before which we were not fully developed, and after which we are prone to biological decay. All right. So think about the strength of G factor and IQ, and where we reach the apex, so to speak, when we become the more flexible, or rather than flexible, when we have the perfect combination of fluid and crystallized intelligence. We are top of the top. We are flexible enough, neurologically speaking, to absorb more information, but we are also able to retain them and have solidly based theoretical assumption about each of these categories. So this combination between fluid and crystallized intelligence, where as you would expect, fluid intelligence is more coherent with earlier stage of development with young adulthood, and crystallized intelligence is more present, of course, in later stage of development with late adulthood and so on and so forth. So on one side, you have this conceptualization of self. And then, of course, you have esteem. So in self-esteem, you have the estimation, the estimate, the ability to relate to someone else in order to have a solid comparative mechanisms. Now, what is this so important from the perspective of evolutionary neuroscience? Well, it is important because if you judge yourself by evolutionary comparison to different elements around you, those different elements are really different people. So you might have a low self-esteem if you think less of yourself. You might have a high self-esteem if you think high of yourself. Now, I'm somewhat skeptical about the whole self-esteem endeavor in modern pop psychology, I would say. And one of the things that I'm really critical about, I mention this all the time, is that certain recommendations that you find in pop psychology are very superficial and also quite detrimental. Some of these advice may be, well, as long as it makes you feel good, then it's good for you. I think this is one of the most misplaced and disingenuous advice that any psychologist could give, because your whole sense of self is predicated upon a constant evolution. You want to become a better version of yourself. Now, the danger, of course, is to compare yourself to others. You really need to focus on yourself and the previous version of your external and internal manifestation, rather than think that whatever stage you're in, that's it. Now, this has nothing to do with finding this inner peace that is predicated upon things such as meditation, mindfulness, prayer, awareness, gratitude. Those are wonderful things. But if you are struggling, even from the perspective of evolutionary neuroscience, this struggle only serves the purpose to move on to the next stage. There is something that needs to be discovered. So if you have self-esteem issues, in this sense, you need to estimate the otherness from you. This goes back to what we said about Levinas, the concept of the other. So if you have a low self-esteem that you can cognitively interpret, in other words, you're aware of it, it's not buried into your pre-conscious or subconscious states, and you compare yourself to another person, and this other person, for instance, might have a good judgment of you, yet you better accept that judgment, because otherwise this will be counterproductive, or rather counterfactual to the likelihood that you appreciate this person's judgment. If you consider this external person as smart, for instance, and this smart person sees the beauty in you, you better accept that, despite the fact that your own cognitive and emotional state of mind might not be interpreting reality as this other person. Now, this really means another thing that is connected to the discussion of evolutionary neuroscience. Is there a way that we can interpret ourselves in the most nurturing way? And in my mind, the answer is yes. The more you find out about your real nature, the more empowering this realization is. Meaning that your inner core is good, and if you have low self-esteem issues, you might have mistakenly interpreted the self as a whole, or you might have made errors, categorical errors, mathematical errors in the way you estimate the value of this self. So once you realize that, then you find that you don't have to choose between pretending you're something that you're not, or trying to become something you're not simply to, quote unquote, please the external factors. But you will become a better, a more truthful version of yourself. And that's what really evolutionary perspectives have to say about the conceptualization of self. It's a constant process. You're becoming a better version of yourself. So it's not that previous version is worse or is ethically or morally less, but it's simply a previous stage. Everything is part of this sequence. Wonderful. So among the fields or subfields rather that are connected to the discussion that we just analyzed, we think of neuroengineering and neuroimaging, and this is exactly what we are about to discuss in the last part of this lecture. Let's begin with a brief history of neuroengineering. Now, by neuroengineering, we really mean neural engineering, which is a combination itself of multiple theories, and especially from the perspective of what Aristotle would define as techne, so technology, so techniques, technology used in the application for the analysis, monitoring, enhancing or repairing neural system. Now, this has to do with augmentation properties, amelioration, and improvement. But even the history of neuroengineering really is connected to the history of neuroimaging, because the idea is this: we can understand something about our brain if we have a solid empirical evidence to discuss, or at least to utilize in a discussion to prove certain therapeutic points, for instance. Now, when we compare correlation and causation in the context of these neural underpinnings, especially from a human perspective, we have to think about what the primary focus is going to be. And that is, I mean, the fact that neuroimaging is in itself not causal. This is something that throughout the history of philosophy has been apparent, even before the beginning of neuroscience. And that is, I mean, the way you will look at things will determine what you're going to find about things. This has to do, again, with the heuristic perspective. If you remember, we talked about double hermeneutics and anthropogenetics, and we talked about the fact that the observer becomes the observed factor. So when we think about what type of technology to utilize to understand our brain, we also think about the possible outcomes we will be able to determine. Now, in the part of this chapter, we will examine the development and typology of neuroimaging techniques, and we have to think about that there are historical factors that define the beginning of this field. Now, if you really think about the very first neuroimaging technique, we had to think about Angelo Mosso, who was this Italian, interesting enough, physician, but as well as physiologist. He was also a professor, was a center, and even an archaeology professor, archaeologist. So a Renaissance man by definition. So he also invented the sphygmomanometer, the ergograph, the hydrosphygmograph, and the plethysmograph. So his biggest contribution to our field, to the field of neuroscience, more specifically to the development of neuroimaging, came from the human circulation balance, which was invented by Mosso in the 19th century. And this was a technology which allowed for a non-invasive measurement of the distribution of blood during emotional and cognitive activity. Now, this is very interesting because a lot of neuroimaging is still focused on oxygenation level and blood flow through the brain. So this is really essential. Now, so what does that mean? Well, he was able to identify and analyze some of the most important variables still used in modern brain imaging techniques. To give an example, he promoted the experimental and simultaneous recording of multiple physiological parameters, focusing on the signal-to-noise ratio. Now, the main hypothesis here, it's the fact that the connection in terms of direct correlation between processes and physiological activity, more specifically between intellectual or emotional activity and increase in blood flow in specific functional areas, had causal factors. So there is a connection between increase in processes, increase in physiological, increase in psychological, increase in neurological activity, if you can see an increase in blood flow. So those areas in the brain would quote unquote light up if there is more blood flow, and lighting up means that the activity is increased. Now, so from this perspective, functional changes determine alteration in blood flow and organ volume change on a brain level. Now, what Mosso did, he really measured the variation by converting brain pulsation into plethysmographic waves. The studies by Mosso strongly influenced research in neuroscience and psychology, especially in clinical and diagnostic testing. So, if you think about empirical scientific evidence for neurological activities, you have to think about Angelo Mosso. Now, until recently, some of the most important aspects of these studies were almost unknown. A possible exception is a brief mention that William James did in regard to Mosso's work. It's due to the absence of appropriate translation of the original manuscripts, which, as you expect, were written in Italian. And it's something that it's unfortunately part of modern neuroscientific research and science as a whole. It's important to understand whatever we study in a specific language, so it really be proper to at least be somewhat versed in other languages, so you can have a broader scope of analysis if you can read peer-reviewed scientific papers in multiple languages. Now, of course, Mosso was not the only one, and there are plenty of scientists, again, in the mid to late 1800s that were instrumental in this field. And think about Hittorf and Plücker and Goldstein and Crookes and Röntgen. Röntgen, of course, was the famous scientist that led to the use of X-rays technology, and another one could be the pneumoencephalography, which was introduced later on I think the end of the first decade of 1900, I think 1918 or 1919, by Walter Dandy.
Others, Pereira and Sven-Ivar Seldinger, that of course, as the name implies, was the author of the Seldinger wire techniques. There are multiple ones. In modern times, so we think about the 1960s and 70s, you think of CT scan or CAT, so computerized axial tomography, that allow for a combination of multiple X-ray images that were taken from different angles. And those first tomographic techniques were really primitive in a sense. They were a single image and were first utilized in the 1900s by Le Bon. Eventually, they were improved in their technology by Hounsfield and Alan Cormack. And then you have evolution of this type of technology all the way to PET or PET scan, right? Single photon emission computed tomography or SPECT, that are all types of CAT scan, really. Now these develop with a parallel technological advancement with radioactive neuroimaging. In the case of PET, by Lassen, by Ingvar, Skinhøy, as well as Kuhl, Chapman, and Edwards. I'm not expecting any of you to remember all these names, but this is good for a perspective of an overall understanding of how those technologies came to be the most important ones in the context of neuroimaging. Now, the most famous one would probably be after SPECT, although we had to mention that in the case of SPECT that there are several stages of development, because SPECT was first replaced with high resolution computerized axial tomography or magnetic resonance imaging techniques, and SPECT really allows for an analysis of the dynamic brain activity. But the most famous brain imaging technology is probably fMRI, so functional magnetic resonance imaging, which produces an even better quality of images, and it has a plus element, has the advantage of being non-invasive, or relatively non-invasive, and also relatively safe. It's definitely safer for the patient because it does not use radioactive isotopes. Now, in neuroimaging, from the perspective of research, it's important to understand that multiple combination techniques might be used. For instance, you can have PET MRI or PET CT scanner, and there are other common techniques that are more basics, I would say, simply because of their neurotechnological development. For instance, multi-channel electroencephalography or EEG, magnetoencephalography or MEG, and then there are other techniques that are not meant to view or interpret, but to stimulate, to elicit a response. And this is probably best known in the context of transcranial magnetic stimulation, TMS. Now, interesting enough, that this very method derives in itself from the study by Galvani as well as Faraday, and all the way to Tubini and Ciarletti. Now, if we were to compare the use and effects and side effects between TMS and ECT or electroconvulsive therapy, this has been one of the biggest issues at the center of both neuroscience and psychiatry. Now, of course, ECT and TMS are extremely different, and of course, you could also argue that ECT, being the modern version of the so-called electroshock, has a lot of ethical, moral, and societal judgment-based issue associated with that, but in themselves are interesting because they are completely related to studies on consciousness and awareness, and in themselves are relevant because, especially in the context of ECT, the question of where we are when we are not there remains prevalent. So when we think about anesthesiology as a primary field before the application of ECT, the question still remains intact. Now, one of the things that I also want to point out is that there are a series of observations on observations to make. Okay, so observations on observation, because again, neural imaging is by definition observation alone. Neuroimaging is truly neural imaging, and thus contains images of neural activities, not necessarily those activities themselves, okay? And this is exactly what philosophers such as Bloom pointed out, all right? Now, which really means that there can be some empty statement when we talk about causal factors, okay? So there are two different targets. Target A is rationalism, with the emphasis on the etiology, diagnostic, and symptomatology, thus focusing on the causal mechanism, inclusive anatomical observation, as in neuroanatomical analysis, okay? So what you observe. And then there's target B, which is embodied by empiricism to connect with possible prognostic and clinical strategies in the context of neuroscience applied to medicine, psychiatry, and psychology. This has to do with the very concept of pyramid of evidence, okay? So one of the issues is that there might be a confusion between what we observe and the claim that what we observe is the activity, okay? Monitoring something, it's not this something alone, okay? Aside from the fact that our observation might change its patterns, but we cannot claim that neuroimaging constitutes the whole truth about those very processes that we are observing. In other words, a good example, without thinking about neuroscience, could be I'm going to use an extreme example. Is a love poem or a love song the same as love? Now, of course, it might be better, worse, but definitely different. It's not exactly the same thing. The same way as reading a recipe, right? It's not the same as the food we're eating. Not even the process of eating, the experience of eating, it's anywhere close to what you can read by reading the ingredients. Or describing a painting, it's not a painting itself, despite of the fact that you can be extremely precise in discussing shape and forms and structure and strokes and colors down to the very minute detail, and yet it's not the experience itself. Now, there's another factor here, that the experience themselves might not be the ultimate layer for what the truth behind the experience is. In other words, we may have subjective experiences that are different, that are all linked to the ultimate truth of that experience. Example, we can all watch the same movie, but each of us will have a different experience about the movie. So neither someone telling about our experience is equivalent to our experience, nor all the combination of our experiences might make the movie itself. So when we think about neuroimaging, we have to think about an observation of what's happening, okay? A very warranted one, but nevertheless different than the activity itself. Now, to continue with our discussion, we have to think about the concept of the average of the averages. So the very fact that we can monitor things and have a solid understanding of what the most common, as in normal function is in terms of statistical analysis, but it's not exactly the same as each element. Now, for instance, if you think about, I don't know, a good example that I use very often is to think about what it means to have a mean, a mathematical mean, or even an average. Think about having a foot in a bucket full of burning flames of some sort, and the other foot in bucket full of ice. Now, the average between these two experiences will be the fact that you're just fine, but the truth is that you're going to burn on one side, you're going to be frozen on the other side. So the average doesn't really contain all the perspectives, especially in the context of neuroscience, where human experience plays a central role. But even more so, we think about consciousness. Now, this is a field that is extremely complex, and we will continue discussing that in this course. But consciousness can be interpreted through a variety of lenses or perspectives, computational, cognitive, and so on and so forth. And yet, to claim that consciousness is directly connected to brain activity, when connected we mean cause, well, that's where we might have a big problem in making that claim. So let's see what we mean by consciousness, and if there's anything within medicine that we can relate this term to. Now, one of the things that for sure we can think of it is consciousness as level of awareness, right? And whether there are different levels or stages to this awareness. So is there such thing as a series of stages of consciousness? Now, there are plenty of theories, and in the textbook we mentioned but a few. For instance, IIT, or Integrated Information Theory, which is the one developed by Giulio Tononi. The Orch-OR, the orchestrated objective reduction by Penrose and Hameroff. You might have heard this before. Roger Penrose and Stuart Hameroff are instrumental in the discussion of microtubules and the role that this substructure play in the development of awareness. And of course, Stuart Hameroff comes from the perspective of anesthesiology, so physiology and medicine, of course, versus Roger Penrose comes from a solid experience in mathematics, theoretical and applied mathematics. So this is one of the very interesting model. Then you can have the holonomic brain theory by Pre-Bramenbaum, and you have other combination of perspective. And the one that I mentioned here briefly are the one by David Chalmers, by Damasio, by Metzinger, by Edelman, by Michio-Kaku, by Koch, Pinker, Popper, Roth, and many others. Now, this is of course connected to what we mean by perception and cognition. And every time we think about perception and cognition, we think of altered state of mind and perception. And this in itself could be the center of a whole 15 weeks course. So for now, one of the things that I would like students to remember is the difference between labels that we use in medicine to define different stages of consciousness, where consciousness is to some extent an equivalent of computational awareness from the perspective of medical treatment and therapy. So those terms are LIS, or locked-in syndrome, minimally conscious state, persistent or continued vegetative state, so PVS or PCS, chronic coma, and brain death. Now, very quick here, but by LIS or locked-in syndrome, we indicate a subject as being isolated due to quadriplegia or pseudopulmonary palsy, albeit having awareness, sleep-wake cycles, and clinical meaningful behavior. In a specific case, the syndrome is classified as total locked-in syndrome, and the acronym is pretty straightforward, so TLIS, or completely locked-in state, CLIS. Of note, in LIS, the eyes of the patients are paralyzed as well. So there was a term that was first used by Fred Plum and Jerome Posner. Then in minimally conscious state, the patient has intermittent periods of awareness and wakefulness and displays some meaningful behavior that is demonstrating purposeful or voluntary behavioral responses to auditory, tactile, visual, or noxious stimuli. In PVS or PCS, you find an individual that is being given a clinical diagnosis in which a wakeful and conscious state lasts longer than a few weeks with no evidence of sustained, reproducible, meaningful behavior, as well as no evidence of language comprehension and or expression. Intermittent sleep-wake cycles, sufficient preservation of autonomic functions to permit survival with adequate medical care, bowel and bladder incontinence, variable preservation of cranial nerve and spinal reflexes. Furthermore, subjects in this stage, so again PVS, PCS, are not aware according to three factors, and these are really important. I would like you to remember them, although they will not be present in any specific assignment. It's really important to understand what do we mean by that. So A, the presence of stereotypical ocular, facial, and motor movements seen only with the destruction of higher cortical structures, and again, the discussion of the cortex here is fundamental. Accompanied by the absence of any voluntary movement, and by voluntary, of course, we still are connected to the free will debate. B, PET studies that show decreased glucose metabolism in these patients, and finally C, post-mortem autopsy studies showing extensive structural damage that is probably incompatible with consciousness. Now, of course, here you see again this incompatibility. This it's quite unlikely that. Now, this is of course a big statement, because the assumption is that everything about consciousness is in itself part of the brain. And this still remains to be seen, not seen from a medical standpoint. Evidence simply means that it has to do with what you can observe. And yet, two things. First of all, what you can observe is either due to possible sensory fallacies, because we rely on our senses, even in the case of mechanisms or technology that we ourselves develop, because all our technology, in the end, whether they're based on specific algorithm or not, is still man-made. By man-made, I mean human-made. And the other thing, there might be something that is really hard to account for in the context of what is usually referred to as
out-of-body experiences or near-death experiences, for which I recommend the review of the links below. But let's continue with our labels here, our descriptors. Coma, chronic coma, often simply referred to as coma. This state indicates lack of consciousness and awareness and sleep-wake cycles, failure to initiate voluntary actions, displaying only reflective behavior, and to respond normally to stimuli such as light, pain, and or sound. Finally, brain death. It's a clinical, medical, ethical, and legal definition upon which multiple debates are still trying to provide clarifying attributes. Now, in general, by brain death, we indicate a full and complete loss of brain function, including involuntary processes required and necessary to sustain life. And this requires a certification process, including, and this is the legal, medical, and ethical perspective. Number one, identification of history or physical examination findings that provide a clear etiology of brain dysfunction. Number two, exclusion of any condition that might confound the subsequent examination of cortical or brainstem function. Number three, performance of a complete neurological examination, including the standard apnea test and 10 minutes apnea test. 4, assessment of brainstem reflexes. 5, clinical observation compatible with the diagnosis of brain death. 6, responsibility of physicians. Number 7, notify next of kin. Think about the multidisciplinary treatment team. Number 8, internal observation period. Number 9, repeat clinical assessment of brainstem reflexes. 10, confirmatory testing as indicated. And finally, 11, certification and brain death documentation. So all these factors really are connected to the main core of this course. So mind versus body, or mind with the body, and whether consciousness can be really interpreted from the perspective of brain and brain alone. Now, we'll mention this throughout the course because it's really a subtitle for the course, Critical Neuroscience, the mind-body connection, or the mind-body problem. Now, among the things that are relevant is the assumption that what we observe at the brain level is what we observe at the conscious level. Now, and one of the things that you can verify on your own is whether things such as field theory is relevant to the mind-body problem. And of course, within field theory, we usually utilize field theory in physics, in quantum physics, of course, and we verify whether field theories of consciousness make sense in terms of the same theoretical mathematical constructs. And one of the issues in this context is understanding whether we can have anything at all that's measurable. Now, anything at all, we really mean mathematically speaking. They have solid numbers to monitor consciousness. And usually when we have numbers, we have to give ourselves at least certain parameters. And we think about physics, well, those parameters have to be the usual time and space, whether it's something along those lines, and whether time and space are in themselves connected. And we find out that, first of all, we might monitor consciousness from the perspective of certain levels of development, so more or less stages, and this is really the computational analysis. So consciousness as an increased capacity or ability, I would say, although this doesn't mean self-capacity necessarily. By self-capacity we mean there might not be a level of agency or self-autonomy or even self-awareness of the process. We simply mean that there is some level of abilities, okay, of skills, cognitive skills. More means an increased level of consciousness, less means a decreased level of consciousness, all the way to absence of consciousness, and those labels we just mentioned, all the way to brain death. And yet, this only means what we can relate to as consciousness by observing the brain. We do not really have the capacity to say that this exists in the brain alone, okay? Or whether the brain is in itself just as a radio transmitters, that it's able to convey certain messages, but the messages exist independently from the brain. That the usual metaphor that they use at the beginning of this semester, where you could view as consciousness or as the self as, I don't know, a music performer, as an artist that you can hear over the radio, and if the radio itself does not work properly because of intrinsic inner problems, there is some sort of technical glitch or issue at the radio, or internal and external problems. For instance, you might have some static that doesn't make the music as stimulating or pleasant to your ears, but this has nothing to do with the performer themselves, or that has nothing to do with the host. Okay, so it might be a problem with the radio. Similarly, when we think about consciousness, we can certainly monitor consciousness in the brain, and the brain is the primary filter that allows consciousness and awareness to be filtered out and filtered in. We have the ability to recognize a human being as such through the brain, but to claim that the consciousness exists on the brain, that seems to be that is an assumption that by definition does not find empirical evidence, the empirical evidence of which is only predicated upon the existence of the brain as primary causal factor. And one of those things are really relevant when we think about fields of consciousness and whether consciousness is cannot be interpreted temporally speaking. So there's no level of space. We cannot really point out to consciousness as existing in a specific area unless we have secondary observation. For instance, what we just said, we can say that a part of the brain is more conscious simply because we can see an increased blood flow. That's what we said about Angelo Mosso and the earlier techniques of neuroimaging. But whether that consciousness is not diffuse, we cannot make that claim simply because there are different levels of self mnemonic patterns too. For instance, think about memorization processes, the fact that we can recognize ourselves as ourselves in a picture taken when we were, 5 years old, and we can still recognize that we are the same person when we are 10 years old or 12 years old, despite the fact that we might dress up differently, we might have a different aesthetic presentation, different clothing, different hairdos, and so on and so forth. So we recognize ourselves throughout time. Now, if we think about neuroengineering, these techniques, of course, have only to do with the brain, or at least with this embodied causal factor, so with our bodies. And we mentioned the nerve growth factor, we mentioned the research by Montalcini, by Hamburger, by Coma, and so on and so forth. And I would like to conclude this lecture with the very last portion of neural imaging. And this has to do with what type of techniques we utilize to investigate and develop the implementation of growth factor and regeneration of brain structure, of body structure. Think about cell adhesion molecules, stem cells, and olfactory acidin cells as viral or non-viral factors. Now, whenever we think about stem cells, there's always a series of ethical challenges, and by no means this course can address all of these challenges and all the parameters, because if we think about stem cell research, an important thing to keep in mind is that we're not dealing with random molecules, okay? Whether random molecules exist as a construct, but we're dealing with cells, and again, non-random cells, but human cells. And of course, in this context, the biggest issue is that these cells might or might not contain embryonic human stem cells. Now, there are multiple scientists that we should quote when we think about this research. Think about Haeckel and Capecchi and Thomson. Capecchi was awarded the Nobel Prize in Physiology or Medicine for the knockout mice discovery and the knockout mice method. So this had to do with creating mice in which a specific gene is turned off. And he was really the first physiologist, the first scientist to create the first human embryonic stem cell line. And there are many other important names, but there are specific definitions that we need to keep in mind when we think about this type of research. And in the book, we just mentioned 3: scientific definition, study on molecular, laboratory, and animal level, and finally, possible application on human subjects. Now, we need to remember that the main controversy on stem cells is related to research in human subjects. And of course, its application in therapy and the moral prerequisites and outcomes in social arena. Now, this is also connected to the very definition on when and how and where life starts. All this from the developmental standpoint as well, from the philosophical, transcendental, mystical, theological perspective, and how biological life may be created
from the soul. Okay. Now keep in mind that the term animal, of course, comes from the Latin word for soul, anima, right? Now, just to sum up, in adults there are 4 main areas where stem cells can be obtained. More in particular, adipose tissue requiring liposuction, bone marrow requiring harvesting or extracting, blood in general requiring apheresis, and umbilical cord blood requiring extraction right after birth. Now, although the research, use, and application of stem cell extraction in these areas are not immune to complex scientific, ethical, and social debates, the biggest controversy actually deals with one specific form of stem cells, the embryonic cells, which are especially important as they are pluripotent and therefore potentially able to differentiate into any of the 3 germ layers developing embryogenesis: endoderm, mesoderm, and ectoderm. Now, this is really connected to what we just said earlier about neurogenesis, neuroplasticity, and the fact that there seems to be a life force, a creative path that underlies everything that exists from a biological standpoint. And I don't think I'm pushing too much in claiming that this element has some sort of spiritual, I dare to say sacred element, as in sacred life. Now, of course, you might interpret sacred as a theological term or religious term, but sacred really means, from this perspective, separated from the rest. Okay, so there's a special element that is predicated upon the function, a function that can take on multiple roles. So as if life is life itself, and then it can take on different clothes, for instance, depending on which type of further development this cell, as an example, will become. Wonderful. As we are approaching the very last few minutes of this lecture, everything we shared so far has to do with our attempt to provide solid biological evidence for everything that is a neural underpinning for the discussion, whether it's neural underpinning of behavior, neural underpinning of emotions, cognitions, awareness, and consciousness. Now, everything we said so far is, I would say, less up for debate, simply because we have sufficient scientific technologies to verify the existence of all these processes. Now, this does not mean, however, that these processes are all there is, because this one will really be addressed starting week 5, right? But it's important to master those basic pieces of knowledge to understand what the brain is actually doing, okay? In the mind-body connection process, we have to really focus on the brain first, okay? Because it's the neurological basis, is what we can all agree upon. Now, in this context, though, we will also have to better understand what we just said regarding the existence of a possible field of consciousness, the theory of field of consciousness, and whether fields of consciousness have any validity in terms of theoretical approach to investigate human awareness, human existence, human ontological reality. So again, we can account for consciousness. We can measure the neural correlates of consciousness from a computational standpoint if we can focus on some level of connection between time and space, where time is simply the passing of seconds, milliseconds, minutes, and so on and so forth, and space has to do with the amplitude of certain waves. For instance, you can monitor rate coding, the spikes rates, or you can use temporal coding, the selective reinforcement of spike coincidence active neurons and network, so that you can combine time and space simply for these neural correlates. But the question remains, is this really consciousness? The question is really not just a philosophically constructed question for the sake of a poetic debate on what it means to be human. It has a very solid rationale behind it, and this is, so far, nobody was able to demonstrate how consciousness arises from matter alone. Now, on one side, you have the whole debate on whether consciousness can account for itself in a rational, ethical, social even standpoint, whether
we have enough judgment that can originate from matter, but even less than that, the very fact that we have consciousness, it's nowhere to be found in the level of space. We can find it throughout time, and this will be one of the maybe primitive, somewhat naive way to interpret that. I understand who I am. I understand my own conscious process, similar to some extent to the I think therefore I am throughout time, based on all my experiences on a continuum, right? That I can identify myself based on what we said earlier. I can recognize myself at different stages of my development. And yet, so far, matter was not able to determine the origin of consciousness. You cannot find any solid rational evidence of this mechanistic explanation. So in our mind, this is at least not logically coherent. In fact, it's a false assumption to make that we find consciousness through biology. Also, there's another factor here, that the very parameters according to which we interpret biology are not self-evident through biology, but they are constructed from fields such as mathematics, physics, and by that I mean theoretical mathematics, theoretical physics, all the way to philosophy. Matter itself does not account for either its own existence or its own parameters of development, origin, and functional structural components. So I would like to conclude this for now with this idea of the false assumption that we can find rational reasons to claim that consciousness originates from matter alone. Thank you again. This concludes week 4. We will see each other again in week 5 between psyche and mind. Thank you very much. Until next week. Bye-bye.